got to the last chair. I was already trying to articulate an answer by looking at space economy and space things, but again, I'll take different questions later if you want. Actually, some of other speakers earlier have talked about space and flight, so hopefully this is a good starting point for me. I work in a company, Thales Alenia Space here in Turin, and we build basically module for human exploration of space and also robotic exploration of space and also scientific payloads. So it's a very interesting perspective. Hopefully the goal of today's presentation will be to share with you the journey that we are undertaking to return humans to the moon and how mobility plays a big role in serving as a mean for these future missions. Okay, so let me start with a very, very basic thing, which all the aerospace engineers start with. That is first flight, and then 60 plus years later, we took the first flight on the moon, and then the first flight on Mars. Of course, we're talking about vehicle and transportation today, so I thought about putting some reference about the first car that drove on Earth, first car that we call rover on the moon, and then the first rover on Mars. As you can see, the last little bit more than 100 years, we've done a huge, huge step forward to go from the Earth to Mars. What we're going to focus today is going to be the moon, and that's because right now human exploration are aiming on returning onto the moon. And eventually one day we're going to see some humans on Mars. This is the first rover that ever went across a different celestial body other than the Earth. This is the LRV built by NASA. It even had a plate on it. Not sure if it had car insurance when it was used, but it was very well designed, flawlessly went through all the missions that it was used for, and it enabled some really interesting scientific discovery. Just for example, I'm showing here on the left, there is the map that Apollo 14, which was the last Apollo mission that didn't use the LRV on the moon. The astronauts walked 1.5 kilometers uphill to visit the crater and then returned back to the landing site to return to Earth. Starting from Apollo 15, Apollo 16, and Apollo 17, that's the last mission that ever took humans on the moon, they used the LRV. And as you can see, they were able to go across more than 35 kilometers on the moon. So the service that the mobility provided was basically driven on scientific aspects. So that's amazing starting point for us when we talk about mobility on another celestial body. This is the map of the moon with the 6 different missions that occurred on the moon's surface. Only 12 men have walked the moon from 69 to 72. Well, Apollo 13 is not on the list, as you know. They had to return back to Earth for issues. But we know that area. We've been there before. After more than 50 years, we will be back on the moon on a different region, which is the lunar South Pole. This is the map of the lunar South Pole. You see there is an arrow there that will indicate where the lunar South Pole is. And these are the 13 regions that NASA has selected as potential candidate location for the future missions on the moon. They are regions of about 15 kilometers by 15 kilometers, so they're pretty wide. And NASA is willing to take humans on each and every one of these regions and explore the entire region during the mission. So the mission is going to last approximately 7 to 30 days. The difference between the Apollo mission and the Artemis missions are that the assets that we are going to build will be used eventually from one mission to the other. The LRV that we saw earlier was one module used only on that mission and then left behind. We are now building, we are trying to build and design and build eventually some new assets which NASA will use during the entire evolution of the Artemis mission. So eventually when we build new LRV options, they will have to move from one region to the other. As you see, there is a long distance to be run from the perspective of these assets. NASA is studying two different options. One is an unpressurized module, which is not called LRV anymore. It's called LTV, Lunar Terrain Vehicle. It's an unpressurized module. Unpressurized means that the astronauts will use this LTV with their suit on, okay? And they will drive around likewise they did during the Apollo mission. But again, this LTV will then be used for the upcoming missions on the moon. And also we have a different asset on the right. That's a pressurized module. Basically, the astronaut can enter the module, take their suit out, and drive around, okay? Both of them are right now under design and study from some of the countries that have signed the Artemis Accords with NASA. And of course, Italy is involved in these design studies as well. We're going to find a very, very interesting place on the moon. From a thermomechanic perspective, we do have some indication from the LRO that is orbiting the moon about the characteristic of the terrain. Of course, no humans has ever been in the lunar South Pole, so right now we have to rely on the images that have been taken from above the surface of the moon to understand its characteristic. But just to mention a few, we do have regions where the gravity is not homogeneous on the moon. So wherever we move something on the moon, we have to consider that gravity is not the same everywhere. We have regions where we can find water. For example, this is the lunar South Pole that we saw earlier, and we have indication that there is water there. So we want to go there just because there is so much water that we can use to build up the Artemis base camp at the end of the day. And also another important characteristic is the elevation. On the moon, the highest point is higher than 10.5 kilometers, so higher than the Everest. And the lowest point is deeper than 9 or 10 kilometers. So the elevation from the bottom point to the highest point is more than 20 kilometers. So wherever we build something that is going to move on the moon, we have to consider important slopes. Of course, there are no roads, no indication about how we are going to find terrain that we have to drive on. The environment is pretty harsh. Temperature goes from minus 150 at night to plus 150 during the day. Of course, there is no atmosphere to compensate for the variation. The cosmic radiation is going to make our life pretty tough. So astronauts can only stay there for a few days and then they have to come back because there is no protection to radiation on the moon. And then this picture reminds us about the dust. All the lunar surface is covered by dust, and this dust is crazy. It's sharp, it's stinky, gets everywhere, and it's going to ruin mechanisms and the suit, and also it's pretty dangerous for the health of the astronauts. Communication and navigation, it takes 2.5 seconds to send a signal from Earth to Moon and receive a response back. So we have to take that into account. Mobility solution will have to run autonomously on the Moon when we send them. And this is also going to take advantage of navigation perspective on the Moon that right now we are really deeply studying to make sure that we can put an asset there that is able to drive around. And lastly, illumination. So this is a video that shows the illumination condition at the lunar South Pole. The Earth is represented upside down because we are going to be the lunar South Pole. And the sun, when it rises and it goes across the sky, never reaches a couple of degrees from the horizon. So it's very, very low. And the sun is going to be our source of energy. We're going to charge our batteries using solar array through the sun. So it's important that we consider this illumination condition. And even the smallest rock on the moon will project a shadow that is very, very long. So when we use mobile asset on the moon, we have to take care about illumination as well. Okay? We have done here in Turin a lot of research on some of the technologies that will enable us to return on the moon and put some mobility asset on the moon. Starting from the top left, you see the ExoMars project that we did with ESA, with the European Space Agency. Of course, it's a rover, so we learned a lot from that project. We had another project with ESA on the moon rover, top right side of this chart, where we have built prototype that we're using today. And then here at the bottom you see on the left another mock-up that we are using for docking. Basically, these assets would dock together with other assets on the moon, so we have to test that technology as well. And what it's much closer to what is going to come to the next chart is what you see bottom right side, which is a pressurized rover that we built as a prototype there. And final chart. We are working together with the Italian Space Agency, which signed the Artemis Accord with NASA, to design and develop the first habitat on the moon. So the first house for astronauts on the moon. You see here on the left, there is a house that is actually sitting on some leveling legs. But our idea is to apply mobility to this concept. So basically, remove the legs, put some wheels on it, and take this house around. Because as you saw earlier on the map of the lunar South Pole, we want to visit every region. So the astronauts will find their house in the different region compared to the mission before. It's a very challenging project. As you can expect, no one has ever done anything like this in history. So it's very, very challenging. We do believe, however, that what we are trying to achieve today not only will enable these future missions on the moon and then eventually build our technology and our experience to go to Mars, but as our vision at Thales says, we're trying to do our best to make a better sustainable life on Earth by doing this kind of research on extraterrestrial bodies. Okay, thank you very much.
Thank you to all our speakers.